Well, students, our next discussion is on Gerschgorin theorem. This is an interesting theorem which can be used as a tool to localize the eigenvalues of a given matrix. What is meant by localizing the eigenvalues of a matrix? Let us try to understand it. Well, Gerschgorin theorem can be used for matrices which has complex eigenvalues also. In that sense, Gerschgorin theorem is more general. As far as our study of power method is concerned, we always assumed that the matrix that we deal with are having only real eigenvalues. In this section, when we are studying Gerschgorin theorem, we will also consider matrices which has complex eigenvalues because Gerschgorin theorem can be used in such cases also. Coming to what is meant by localization, Gerschgorin theorem gives us n disks. If you give a n cross n matrix to it, these disks are basically in complex plane in such a way that all your eigenvalues are located only in the union of these disks. That is what we meant by saying that it localizes, means it just packs these eigenvalues in smaller disks, and thereby we can locate at least roughly where these eigenvalues lie in the complex plane. Well, this tool can be used in a restricted way to decide whether the given matrix has a unique dominant eigenvalue or not. We will come to that part later. First, let us precisely state the theorem, and we will also prove one part of the theorem which is rather simple to prove. Well, the Gerschgorin theorem states that if you have an n cross n matrix, you define n positive numbers like this. How are you doing it? Suppose you have A11, A12, A13, and so on up to A1n. That's the first row of your matrix. You leave the diagonal element. You take all the non-diagonal elements, take their absolute values and sum them up. That is what is denoted as row 1. Similarly, take the second row, A21, A22, A23, and so on up to A2n. Again, leave the diagonal element, take all the non-diagonal elements, sum them up, and that is what is called row 2, and so on. Okay, that is what we are writing here. Well, this should be j equal to 1 to n, and you exclude j equal to k, and k is the index running here for the row and j is for column, and you are just removing the column equal to row, thereby you are excluding the diagonal part. And all non-diagonal elements, you are taking the absolute value and summing them, and that is denoted by row k. Now, we will consider this as the radius of one typical disk that we spoke. So, let dk denotes the closed disk in the complex plane with center as that diagonal element, right, akk, and radius as rho k, which we denoted here. That is, dk's are precisely given by this set, right? Now, what Gerschgorin theorem says is that each eigenvalue of A lies in one of the disks. Suppose you have n disks. Let's imagine there are 5 disks. We are working with 5 cross 5 matrix. Then each eigenvalue of A lies in one of the disks. Your lambda 1 may be lying here, your lambda 2 may be lying here, lambda 3 may be lying here, lambda 4 may be lying here, and lambda 5 may be lying here. What is interesting here is that none of the eigenvalues of your matrix A will lie outside these circles. This will never happen. That is what the statement says, and this is yet another important point that one has to keep in mind. Suppose that among the disks D1, D2 up to Dn, as I drew previously, suppose you have 5 disks, you are working with 5 cross 5 matrix, you have 5 disks, there is a collection of M disks, that is, say M is equal to 3, whose union is disjoint from the union of the rest of N minus M, which is 2, right? So this has union of 3 disks and this has union of 2 disks. That's what here it says. Then exactly M eigenvalues lie in R1. So this we are calling as R1 and this we are calling as R2. Since you have 3 disks here, precisely there are 3 eigenvalues sitting here. It can be 1, 1, 1 here, or all the 3 may be sitting in one disk. That much we do not know how they will be distributed among these 3 disks. But what you can surely say is exactly 3 eigenvalues will sit in R1 and exactly 2 eigenvalues which will sit in R2. Both eigenvalues may be sitting in one disk or one per disk. That is not really commented in the statement. It says that R2 will have exactly 2 and R1 will have exactly 3 in this example. In general, it is like you have M disks which are clubbed together and kept one side, and there are N minus M disks which are clubbed together and kept on other side. These two are disjoint. Then you have exactly M eigenvalues on one side and N minus M eigenvalue on the other side, right? So that is what is the second conclusion of Gerschgorin theorem. Here you should also note that each eigenvalue is counted as many times as its algebraic multiplicity. We will prove only the first part of the theorem because it is very simple to prove, and second is omitted for our course. Okay, let us prove the first part. Let us just recall what is first part. Each eigenvalue of A lies in one of the disks. Okay, so that is what we have to show. You take one typical eigenvalue of A, say lambda, and its corresponding eigenvector, say V. And by definition, V is not equal to 0. And it satisfies this homogeneous linear system. Why we said homogeneous? Because it can be written as A minus lambda I times V is equal to 0. So V satisfies this homogeneous linear system. Now let us take the index of V at which the maximum norm is achieved. Okay, so you take the maximum norm of V and see at which index it achieved. You take one such index as R, and how this linear system, that equation will look like. Okay, that rth component of this linear system, how it looks like, it precisely looks like this, where I have just precisely written the rth term like this. Recall it is A minus lambda I, right? V. Okay, so this is the diagonal element of that equation. These are the terms before the diagonal elements, and these are the terms after the diagonal element. Now what I do is I keep the diagonal element on one side, its coefficient, and bring all the other non-diagonal terms to the right hand side and divide both sides by VR. Why I can do that? Because VR is the value which has the maximum absolute value, and since V is non-zero, it has to be non-zero. Therefore, this VR has to be non-zero, right? That is why we can divide on both sides. And now you see V1 is always less than or equal to VR in its absolute value, right? That implies mod V1 by mod VR is less than or equal to 1. And similarly, all these terms, they all in modulus, they are less than or equal to 1, right? So you keep this in mind and take the modulus on both sides. and use the triangle inequality, you get this inequality. In that, each of these terms are less than or equal to 1, right? Because VR is actually coming as that term at which the maximum norm is achieved. So what you can do is you can just use this fact and write this as less than or equal to mod AR1 plus dash 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 plus mod AR R minus 1. Up to here is the part that comes before the diagonal element, and this is the part comes after the diagonal element. Up to, yes, that is what we are writing here. Observe that this right hand side is precisely what we defined as row R, right? Therefore, you can see that your lambda belongs to the disk whose radius is this and center is at the diagonal element ARR of the rth row of the matrix A. So that proves the first part of the theorem. As I told, the second part is omitted for our course, but the statement is very important. We have to keep the statement in mind, but proof we can omit. Okay, let us see an example. Let's take the matrix A as 4, 1, 1, 0, 2, 1, minus 2, 0, 9. Now, let us construct the Gerschgorin disks. What is meant by Gerschgorin disk? This D1, D2, D3 are called the Gerschgorin disk. The radius is obtained as taking the modulus of each non-diagonal elements and adding them. So the first disk radius row 1 is nothing but 1 plus 1, which is 2. The second Gerschgorin disk radius row 2 is going to be 0 plus 1, right? That is 1. And the third disk radius is row 3, and that is given by 2 plus 0, which is 2. Now, what is the center of the first disk? Center of the first disk is going to be the diagonal element of the first row, and therefore it is going to be 4. And similarly, second disk center is 2, third disk center is 9, and thereby the Gerschgorin disks are given in the set theoretic notation like this. We can easily draw the picture of these disks. Say this is 2 and you have radius 1, therefore it is, so this is like this. Assume that it is a circle, and 4, and the second disk center is at 4. Sorry, this is D2, that is second disk, and first disk center is at 4, and the radius is 2, and therefore you have the disk D1 like this. Then you have 7, 8, and 9, and it goes with the center as 9 and radius as 2, so it will be something like this, 10 and 11, right? Now what Gerschgorin theorem says, you have two eigenvalues in the union of D1 and D2, and you have exactly one eigenvalue in the disk D3. If you order them like this, lambda 1, lambda 2, and lambda 3, you can clearly see from the Gerschgorin theorem that without computing the eigenvalues of this, just by seeing the Gerschgorin disk, you can see that you can use power method for this matrix. At least with respect to one hypothesis, that the dominant eigenvalue should be unique. At least that hypothesis is verified using Gerschgorin theorem, right? And another interesting part in the Gerschgorin theorem is that it also gives you a bound for your eigenvalues. How it is so? From here, you can see that mod z minus 4 can be greater than or equal to mod z minus 4, right? And that is less than or equal to 2. That implies mod z is less than or equal to 6. Similarly, this says that mod z is less than or equal to 3, and this says that mod z is less than or equal to 11, right? So that is what I have written here. Gerschgorin circle theorem is helpful in finding bounds also for your eigenvalues. So in the above example, we have from the disk 1, you have this bound, as I told here, and from the second disk, you have this bound, and from the third disk, you have this bound. Combining these three information, you can say that all the three eigenvalues will be in such a way that their absolute values are less than or equal to 11. That we can say, right? So this is what is called the bound for the eigenvalues that the Gerschgorin circle theorem gives. As I already remarked, the main disadvantage of power method is that if a given matrix has more than one dominant eigenvalue, then the method may not converge, right? That we have seen in the last class as hypothesis 1 of the power method. So for a given matrix, we do not know whether the power method will converge or not, right? Because we don't have this information whether the matrix has a dominant eigenvalue or not. At least from this particular hypothesis point of view, we have some limited scope that we can draw the Gerschgorin disks and see. If we are lucky, you may get the information from the Gerschgorin disk theorem that it has a dominant eigenvalue, but it is only restricted. Not always we will get. In the above example in particular, yes, we got it, right? See, this is in particular very useful because we have also seen in one of the examples that the power method converges very slowly. Therefore, you don't need to go for the real-time computation to see whether your power method is converging or not. Okay, so sometimes what happens is it may go for several iterations which may pretend as if it is not converging, but later on it may converge because generally power method converges very slowly. We have seen that. Okay, therefore, if you just want to computationally see whether power method is going to converge or not, you really have to do a very large number of iterations. But if you are very lucky, Gerschgorin theorem may be used to conclude, at least from the hypothesis 1 point of view, whether you can really go for the power method or not. So in that way, Gerschgorin theorem is very interesting and useful for those who uses power method. We can also have a slightly different perspective of Gerschgorin theorem, which often helps us to get a better localization to the eigenvalues of a given matrix. The idea is to use A transpose instead of A in the Gerschgorin theorem. Let us take this as a corollary. Note that other than this small change, rest all remains the same as we have done in the Gerschgorin theorem. Let us formally state the corollary. Let A be an n cross n matrix. Now, you apply the idea of Gerschgorin circle theorem to A transpose. By that, what you will be doing, you will be fixing a column, say kth column, and you have a kk as the diagonal element. Now, you will run across all the rows of this column and take the modulus of each of the element in that column and then sum them up, excluding the diagonal element, right? So if you recall the same in the Gerschgorin theorem, when we go to apply the theorem for A, what we did, we fixed the row and ran across the columns and took the modulus, leaving the diagonal element, and then summed them up, right? So this we called as row K, and now we will use the notation tau for this idea of applying the Gerschgorin theorem to A transpose. Therefore, tau K is defined as J equal to 1 to n summation A. Now J runs in the first index of A, which corresponds to rows, right? And leaving the column index fixed. So that is the idea of the corollary. And now you define the Gerschgorin disk with radius as tau K. And that we will denote as Bk. Once this small change is understood, the conclusion remains the same. We will write the conclusion for A only, not for A transpose. Of course, we can always write it as each eigenvalue of A transpose lies in the disk Bk. Then it is exactly the Gerschgorin disk theorem. But what we will say is each eigenvalue of A, because A and A transpose has the same eigenvalues. Therefore, we can also tell like this. And that is the main idea of the Gerschgorin theorem applied to A transpose. The second conclusion will also holds exactly in the same way as what we stated in the Gerschgorin theorem. Well, what is the advantage of this corollary when compared to the original Gerschgorin disk theorem? As I told you, sometimes applying the Gerschgorin theorem to A transpose may give a better localization to the eigenvalues. That is the idea. Let us explain this idea in more detail. Let A be an n cross n matrix with R is equal to union of all the Gerschgorin disks obtained by keeping the matrix A. That is how we did in the Gerschgorin disk theorem. And let C be the union of all the disks obtained by keeping A transpose, that is from the corollary. Let us call these BKs also as Gerschgorin disks. There is nothing wrong in that. Now, it may happen, not always, but it may happen sometime that C may be contained in R, in which case you got a better information about localizing the eigenvalues than what we got through the matrix A, right? So sometimes you may not have adequate information when you work with DKs. So what you can do is you can also put an attempt to construct the Gerschgorin disks for the A transpose and thereby look at the disks BK to see whether you can have a better conclusion. That is the advantage of the corollary. Of course, you can always take C intersection R, which is always going to be contained in C as well as in R, right? Therefore, in that way, you can also get a much optimal region that encloses the eigenvalues. And that can also lead to optimal bounds for our eigenvalues. Now let us see how to get this optimal bounds. Well, before going into the construction of optimal bounds, let us see how to construct the annular region in the complex plane that contains the eigenvalues of our matrix. That is, we have to find a small r and a capital R. Don't confuse this R with the region that we defined as the union of the disks. Okay, I'm sorry for using the same notation for both these quantities, where small r and capital R are non-negative real numbers such that this set is what is our interest, where all our eigenvalues lie. How it looks like? So you have a circle with, say, center at Z and radius R, and you have another circle with center same Z and capital R. Then this set is nothing but the annular region, right? So this is quite interesting to see how to construct such an annular region from the Gerschgorin theorem that contains all our eigenvalues. As usual, let us take A is equal to Aij, which is a n cross n matrix, and K is equal to 1 to up to n. We know how to construct the Gerschgorin disks with the help of A, and they are denoted by dk's, right? They are given by the set of all z such that mod z minus akk is less than rho k. Remember, we are constructing the Gerschgorin disk with A, not A transpose. Therefore, we use the notation rho k. You know what is the meaning of that. There is a subtle difference between rho k and tau k. This can be written like this. It's just a generalized triangle inequality, and that in turn gives us mod z minus mod akk is less than or equal to rho k, and also the other way, that is akk modulus minus mod z is less than or equal to rho k, right? Now from here you can write mod akk minus rho k is less than or equal to mod z is less than or equal to mod akk plus rho k, right? I'm just keeping zk and taking this to the other side and getting this, and similarly take this to the right side and rho k to the left side, and that gives you this. That's also a simple manipulation. Once you do that, you can see that you got the annular region in this form where small r is this quantity and capital R is this quantity for one typical disk. And now what you do is you take the minimum of all the lower bounds and maximum of all the upper bounds, right? Note that if R becomes negative, then you replace it by 0, because one can also have R to be negative sometimes. So you can see that all eigenvalues of A are contained in this annular region, right? The same idea can be applied to the matrix A transpose also, and thereby we get another annular region which we denote by Z in C such that small t less than or equal to mod Z is less than or equal to capital T. In the previous case, we had R for this. Now we will just use the notation T, where T, small t is the minimum of all the lower bounds. Now remember, it is not rho, but it is tau now, because we are applying our Gerschgorin theorem to A transpose. That is, as per the corollary, we are now constructing the annular region. And similarly, all the upper bounds you take and take the maximum of that. And you can see that again, the same eigenvalues of A, because they are basically the eigenvalues of A transpose. Therefore, they are eigenvalues of A belongs to this annular region. Now, how will you combine these two annular regions to get an optimal bound for your eigenvalues? Let us see how to do that. Before that, the routine remark is that t may become negative. So you replace it by 0 if t becomes negative. That is just a routine remark. Now you define the optimal or smallest annular region like this, where lambda suffix star is the maximum of R and T. Okay. So you had R less than or equal to mod Z is less than or equal to capital R, and T less than or equal to mod Z is less than or equal to capital T. These are the two annular regions where we had all our eigenvalues. Now what you do is you take these two, take the maximum of this. And similarly, you take these two and take the minimum of this. That will be your optimal bound, in the sense that all your eigenvalues of A will belong to this annular region. And that is the smallest annular region in which you can pack all your eigenvalues, right? Note that this is the best possible information that we can obtain using Gerschgorin theorem. So you should know how to construct this optimal bounds. Okay, we will refer always this lambda suffix star and lambda superstar as the optimal bounds for the eigenvalues as per the Gerschgorin theorem. Then what you do is you find the annular region by applying the Gerschgorin theorem to A, and you also find the annular region by applying Gerschgorin theorem to A transpose, and then you use this formula. Let us see an example. Let us take the matrix 6, 0, 2, minus 1, 5, 0, minus 2, 2, and minus 3. Let us construct the Gerschgorin disk for the matrix A. They are given by D1, D2, and D3, which you can see very easily. Now let us try to construct the annular regions from each of these disks. Let us take D1 first. From D1, we can use the triangle inequality to write mod Z minus mod 6. The full modulus is less than or equal to mod Z minus 6, and that is less than or equal to 2. From here, we can write mod Z minus 6 is less than or equal to 2, and 6 minus mod Z is less than or equal to 2. Now, this implies mod Z is less than or equal to 8, and this implies mod Z is greater than or equal to 4. Both combined together, we can write 4 less than or equal to mod Z is less than or equal to 8. So this is the information we get from D1. Let us see what happens with D2. For D2, again, we can use the triangle inequality to write mod of mod Z minus mod minus 5 is less than or equal to 1. And that can be rewritten as mod Z minus 5 is less than or equal to 1. And 5 minus mod Z is again less than or equal to 1. Combining these two, we can get mod Z is less than or equal to 6, and it is greater than or equal to 4, right? So we got one inequality for mod Z from D1, another from D2, and let us see what we get from D3. From D3, we can write mod of mod Z minus mod minus 3, and that is less than or equal to mod Z plus 3 is less than or equal to further 4, right? And that gives us mod Z is less than or equal to 7, and it is greater than or equal to minus 1. If you recall, we have always remarked that if the lower bound happens to be negative, then we have to replace it by 0, right? So we can take this inequality as 0 less than or equal to mod Z is less than or equal to 7. Now we can go to define our annular region where the lower bound small r is taken as the minimum of all the lower bounds, that is 4 from D2 and minus 1 from D3, which we take as 0, and that gives us 0. And the capital R, which is the upper bound in the annular region, is taken as the maximum of the upper bounds, which happens to be 8 from D1, 6 from D2, and 7 from D3, and that gives us 8. Therefore, the annular region given by the Gerschgorin theorem for the matrix A is the set of all Z in C such that 0 less than or equal to mod Z less than or equal to 8. Now, what we infer from here is that from Gerschgorin theorem, we can see that all the eigenvalues of A belongs to this annular region. It means you take any eigenvalue, complex or real, its modulus will be greater than or equal to 0, of course, less than or equal to 8. Okay, so as long as the lower bound is concerned, there is not much interesting information coming for this particular example for the Gerschgorin disk. Rather, we have an interesting information for the upper bound. Let us go to construct the same annular region for A transpose and see whether we are able to improve these bounds. In the similar way, you can also construct the disks for the matrix A transpose, and from there you can get the annular region. I will not repeat these calculations, but I will just give you the final answer. The annular region that we obtained from the Gerschgorin theorem applied to A transpose is given by the set of all Z in C such that 1 less than or equal to mod Z is less than or equal to 9. Here you can see that you have a better information about the lower bound of all the eigenvalues of A, but we don't have a better information as far as the upper bound is concerned. Why? Because our previous case says that the upper bound is 8, right? So that's a better information that we got than this information. So as far as A transpose case is concerned, our Gerschgorin theorem says that all the eigenvalues of A transpose and therefore A lies between 1 and 9 in their absolute value. That is what we are inferring from here. From here, we have to find the optimal bounds, subscript star, and that you have to take as the maximum of the lower bounds. In the first case, the lower bound is 0, and in the second case, that is for A transpose, we got the lower bound as 1. Therefore, it is maximum of 0, 1, and that happens to be 1. And similarly, the upper bound of your optimal region is lambda super star, and that is going to be the minimum of the upper bounds. You should clearly understand why we are taking minimum here, whereas in constructing the annular region, we took maximum on the upper bound, whereas minimum on the lower bound. So you should just think why we are doing that, and this otherwise you will get confused. Here it is minimum of the upper bound in the case of A and the upper bound in the case of A transpose. If you recall, the upper bound that we got in the annular region in the case of A is 8. Therefore, we get here 8. And here in the case of A transpose, we got 9, right? Therefore, your lambda superstar is going to be 8. And so finally, combining these informations, Gerschgorin theorem says that any eigenvalue of the matrix A will lie in this annular region. It means you take any eigenvalue of A, its absolute value will be less than or equal to 8, and its absolute value will be greater than or equal to 1. That's what it says. And this lambda substar and lambda superstar, these are the optimal bounds. So if I give you a matrix and ask you to find the optimal bounds for the eigenvalues of the matrix A, you have to do all these steps.